Okay. Hopefully that looks good for all of you watching. Really quick, I'm gonna give a shout out to Hefarius for continuing to pump out these awesome articles. And a shout out to also Gonzalo, who recently joined Immunify as a triager for creating the Forge version of this POC, which I'll be using. So thanks to these guys, we have this awesome presentation today. So some prerequisites for this demonstration, if you're going to follow along with the POC. The first one is installing Forge. So we need this to set up our development environment. And the second one is having an archival node for the Gnosis change. The Gnosis chain. And we're going to use Quick Node for that. But we'll get to that later on. Just so you guys know, we're using Quick Node for the archival node and Foundry for our test environment. Okay, so 100 finance heist. What happened? So an overview of the hack. Both 100 finance and Agave lending protocols on the Gnosis chain were hit by re-entry attacks on March 15th of 2022. So what did these attacks do? Well, they drained all of the collateral held in these protocols contracts. So really quickly, let's review what collateral is and why it's typically a juicy target for attackers. So 100 Finance is a lending protocol, which is a fork of Compound. And this protocol just lends tokens to users. Compound is the Ethereum is deployed on the Ethereum chain, and 100 Finance is deployed on Gnosis chain. So when lending tokens to users in the world of DeFi, if we want to lend tokens to some untrusted actor, how can we guarantee they'll pay back their loan? If we say lend 100 Bitcoin to someone who is fully anonymous and just ask nicely for them to pay it back, we would probably never hear from them again. So the way that this is commonly solved in DeFi is a user has to post collateral to take a loan. So collateral is those funds that you're locking into a contract to guarantee the lender, if I don't make payments on this loan and default on the loan, then they can just take the money that I locked in as collateral. Now, if I abide by the rules and eventually pay back all of my loan, I can then unlock my original collateral and get it back. But something else interesting in the DeFi world is you typically have to over-collateralize loans to borrow money, meaning you have to lock something of more value than what you're borrowing. So you may be asking, why would you ever take a loan if you need to over-collateralize it and lock more money than you're actually borrowing? So a couple reasons for that. Maybe the collateral you're using isn't very liquid. Maybe selling the collateral could cause large price impacts. So instead, when you collateralize a loan with an asset, you're essentially doing a swap without selling the underlying asset. This could also give you more exposure to a specific asset by using that asset to borrow funds and then buying more of the same asset with those borrowed funds. I believe you also don't trigger a taxable capital gains event when borrowing, but don't quote me on that. Please check with your tax advisor about that. Yeah, so over collateralization also gives some buffer to lenders and borrowers against price volatility. But yeah, so if the value of your collateral goes below the value of the asset you borrowed, the lender can step in and liquidate your collateral. So they can sell it off and get that in return to cover the loaned, whatever they loaned to you. So to recap, collateral is some asset that you lock to be able to borrow some token. And this means that there's tokens locked in the lending smart contract. So, that's our juicy target for attackers. So lending protocols like 100 Finance also have a few parameters which are needed to allow someone to automatically borrow money. And those parameters are a max collateral amount. So what's the limit of funds we're allowed to put up to borrow? Um, how much can be borrowed against our collateral? So that's our collateralization ratio. How much, which is that's how much above the value of the asset we're borrowing do we need to deposit? An oracle, which dictates the underlying price conversion of the collateral to the borrowed asset, and some kind of health system. These lending protocols typically have some kind of health system where users can only borrow if their health is above some value. So if they have a lot of bad debt, we won't let them borrow anymore. So we'll dive more into that when we get deeper into the vulnerability explanation. But now that we understand what collateral is and why there are just funds locked in this contract, let's get into it. So the root cause of this attack was the post-transfer hooks in non-standard ERC-667 tokens, which enabled reentrancy. So ERC-667 is an extension of ERC-20 tokens, which add hooks that are called on a receiver when tokens are transferred to them. So if we remember, 100 Finance is a fork of Compound, and Compound Protocol was never intended to support non-standard tokens, such as those with hooks or callbacks. On Ethereum, when Compound is deployed, tokens are heavily vetted before being whitelisted. However, on Gnosis chain, the official bridge that Gnosis chain uses creates tokens that have this on-token transfer hook automatically. So ERC-20 token smart contracts are typically very simple and only update balances during a transfer. But these transfer hooks were implemented as a convenience for smart contracts to be able to execute some logic in the same transaction they were sent tokens, rather than having to execute two separate ones. So this on-token transfer hook is called after a token is transferred to an address if it's a contract. If a token is sent to an address that's a contract, the token itself will look to see if that contract implements the on-token transfer fallback, and if that fallback is found, the token will call the contract's on-token transfer function. So this leads to a situation where execution flow of the transaction is given to the contract being called, which allows the contract to do whatever it likes. So for Gnosis chain, this hook was actually intended to be used by the Gnosis bridge contract to prevent users from sending tokens to the bridge by accident. So if we take a look at the code here, we can see this transfer function. It calls this super transfer function, and then this call after transfer. So in this call after transfer, we're first checking that the 2 is a contract. If it is, then we're going to call this contract fallback function. And in this contract fallback function, we do to.call and call this function on token transfer. So this is the function selector here. And this is where we're giving execution flow over to the receiver. Now, if that fails, the contract here checks that the 2 is not the bridge. If it is the bridge, this require will fail and revert. So that's where Gnosis is preventing people from sending tokens directly to the bridge, so that they can go through the proper channels and have that work correctly. So now that you can kind of get an idea of why those hooks are in place, if we remember what reentrancy is, we can start to realize there could be a problem here with 100 Finance integrating Gnosis chain's bridge to tokens. So reentrancy is when a function makes an external call to an untrusted actor before making any necessary state changes. So this allows an attacker to call back into the same function before any of the state variables are updated. An example is a contract where a very simple contract where you just withdraw funds. If the withdraw function sends Ether to the caller using a low-level call before updating the user's balance, execution flow is handed over to the user, and an attacker can call back into that same withdraw function before the contract realizes the balance should have been updated. Okay, so let's kind of take a look at the flow of 100 finance of borrowing tokens and get an idea of where reentrancy may be an issue. So if we look at this image here, we see a user supplies some collateral in any of these markets, which correspond to some asset. And this will then increase your account health since you're locking funds into the protocol. This then reaches out to the controller, which calls out to an oracle and tells it how much that collateral is worth. And 100 Finance allows you to use collateral across markets. So now you can execute a borrow in whatever market after you've posted this collateral. And those borrowed tokens are then sent back from that market to the user. And a global variable tracking your total debt is updated. So if we think about when we can gain execution flow here from the token callbacks, when can we take over and do whatever we want? Well, we see tokens should be transferred by us when we supply collateral, and tokens are transferred when we borrow from the protocol. So in this supply collateral and in this borrow token phase. So it turns out 100 Finance's borrow function is susceptible to this reentrancy. In Hundred's Gnosis deployment, whenever a user borrows collateral, the borrowed tokens are sent before the user's debt level is updated. So when combining that with the on-token transfer callback that bridge tokens have on Gnosis, an attacker is able to re-enter the protocol and borrow against the same collateral multiple times before their debt balance is updated. So an attacker can open an extremely unhealthy position where the collateral is way below the amount of assets they borrowed and just run away with those borrowed funds. So in this case, the attacker deposited around $2 million in USDC as collateral and then borrowed well over $6 million of tokens from many different money markets, essentially allowing them to drain $6 million from the protocol of all available liquidity. So whenever the attacker borrowed a token, the token would trigger that on-token transfer callback in the attacker's contract, giving the attacker the ability to borrow again against the same collateral in another market. So how did the attacker do it specifically? So first, they flash loaned funds. So this allows them to borrow against a very large amount of collateral every time they re-enter the function, and also means we don't need to start with any capital to execute this attack. We don't need to start with those $2 million that we're supplying as initial capital. We can just borrow that too. So after flash loaning the initial funds, they deposit those flash loaned funds as collateral. And this is all happening in a single transaction. Remember, flash loans must be paid back in the same transaction. So we flash loan those funds, we deposit it into 100 Finance. We borrow against the deposited collateral in market 1. And then we re-enter the protocol through the token callback when those borrowed tokens are being transferred to us, and borrow again in a different market, market 2. And since our total debt hasn't been updated and the protocol thinks we haven't borrowed anything yet, it allows us to do this. Finally, before the transaction ends, we need to repay the flash loan with the profits. And we can do this since we run away with basically a multiplier of the amount that we flash loaned originally. Cool. I think that's enough overview of the vulnerability itself. We can go ahead and get into starting to write the PoC. And what will be exciting about this is we'll learn how to flash loan funds from SushiSwap. So that can be reused for other PoCs as well. Okay, cool. So like I said, make sure you have Foundry installed. Go ahead and go to book.getfoundry.sh. Check out how to install, get that all installed. And then for QuickNode, all you have to do is sign up for an account. I'll really quickly show you once you have an account and logged in, if you go to endpoints, let's see if this loads. It's got some issues with quick node. There we go. So once you're in quick node, you go to endpoints. This create endpoint should be listed. I'll go ahead and archive this so I can show you exactly the steps. So yeah, so we're going to create endpoint. The chain we want to use is Gnosis chain because that's where 100 Finance is deployed. We want to select the mainnet network and then continue. And then we want an archive mode node. So that should already be selected and it's included with our free account. So we don't need to change any options here. We can just hit create endpoint. And then once that finishes, our endpoint's created and we're just going to copy this later. Awesome. So those prereqs are set up. Let's go ahead and start coding. So I'm here in a new directory. And my first step is going to be to call forge init. So this is going to set up everything that's necessary for our development environment. It's going to make it a lot easier to run tests, to write code. Yeah, so it sets up all this here, all these files and folders here on the left. We have our libraries, which is any external dependencies, any scripts, which is not important for this POC, the source code for our contracts, and then our test files. So this is what's going to be run. This is our POC that's going to be run. There's also this foundry.toml, which lets you configure some things about Foundry, but we don't need to touch this either for this example. So once we have Forge initialized, the other thing we're going to do first is install some dependencies. So we are going to be interacting with an on-chain contract, which means we need the ABI for that contract. So we need some interface so that our test knows what functions it can call on those contracts. So the first thing we're going to do is we're interacting with ERC20 tokens. So I'm going to install Soulmate, which is a contract library very similar to OpenZeppelin that gives us stuff like ERC20 interfaces. I think it's for just Soulmate. It should be the GitHub repository name. Let me check really quickly. Okay, maybe I need to include the organization, the GitHub organization. There we go. Okay, so yeah, so Forge lets you install dependencies pretty easily by just saying the GitHub org and the repo name. So this is the GitHub org and then the repo name here. So we have Soulmate. We're also going to need some Uniswap interfaces because we're performing the flash loan through SushiSwap. And SushiSwap is a fork of Uniswap and uses Uniswap interfaces. So we're going to Forge install Uniswap /v2 periphery. Oh, forgot to put install. And then we also need Uniswap's v2 core. And when installing these dependencies, it's important that we have no git changes because the command will fail because Forge, when you install something, it creates a commit. So like here you can see we have previous commits, previous installs as commits. So it'll complain if you have any changes. Okay, so now that we have those installed, we're also going to create our remappings, which point our Solidity code to these libraries. So we are going to make a remappings.txt file. And I'm going to go ahead and cheat a little bit here and just copy Gonzalo's remappings. And I'll talk about a little bit about them. So basically this allows us to, in our smart contract, do import at Uniswap / v2 core. And we're telling Forge that that should map to v2 core in our library folder. So it just makes our contracts a little cleaner. Okay, so now that we have our remappings set up, I'm going to really quickly grab our quick node endpoint and export that in our terminal so that's easily accessible later. I'm going to call it fork URL. We're exporting this environment variable fork URL, and we're pasting the API. So that's just for later. Okay, now that we have all of that set up, we can start writing our test. So I'm going to go ahead and follow a design pattern called test-driven design. So we're going to write our test first and then implement the functions we need to actually exploit 100 Finance's protocol. This hopefully will give us a higher level of what's going on. So we're going to modify this test file, which is what's run. I'm going to go ahead and rename this to something like 100 Finance PoC. Let's change the test name as well. Oh, yeah, of course. Is that good? Okay. Yeah, sorry about that. Okay, so we're modifying this test file. All I've done is change the name so far. We don't need any of this that the default template gave us, so we're going to delete all that. We don't need this counter. We do need Forge std test. This is what tells Forge that this is a test and how to run it. So we're going to leave that. But let's go ahead in our test and lay out again what we're doing. So the first thing we're going to do is flash loan funds from SushiSwap. That's our first objective. The next objective is to deposit those funds as collateral in 100 Finance. After we've deposited them as collateral, we can then borrow against that collateral in market A. And then during that borrow, we're going to re-enter 100 Finance and borrow a different asset. Then finally, we're going to repay the flash loan. So I'll leave that there just so we can remember the structure that we want. We're going to go ahead and start importing those interfaces that we're going to need. So we're going to import our ERC20 interface. So Soulmate is the one, remember, that provides us those interfaces, much like OpenZeppelin. So we're going to go Soulmate tokens, and we have ERC20.sol. This will give us the ABI that lets us interact with ERC20 tokens. We're also going to need a Uniswap pair interface. This is how we're going to flash loan those funds again. Uniswap v2 core interfaces I Uniswap v2 pair.sol. So also from the core contract, we're going to copy and paste this. We have we need the factory, which tells us where those pair contracts are. And yeah, sorry, a pair contract is a pool of 2 tokens, which lets you exchange one token for the other. And then we need from Uniswap v2 periphery, we need our Uniswap v2 router. And this will start to make more sense when we start writing our actual attack code. Last thing I'll do is import forge std console.sol. This will let us print out values to the console and makes it a lot easier to debug our test. Okay, so we have the interface for ERC20 tokens. We have the interface for Uniswap. We don't have the interface for 100 Finances contracts. So instead of pulling that from a GitHub repository, we're just going to write them in here. So remember, if you remember, 100 Finance is a fork of Compound, so we can use Compound's interfaces. We're going to pull in interface iCompound token. And the functions we want access to are borrow. And this takes a unsigned integer of 256 bytes. We're going to pull in the mint function. This allows us to mint our 100 Finance asset. And we're going to pull in the comptroller. Okay. We'll start with this for now, and just start writing our test and write more interfaces as we go. So our test. So let me go ahead and go back to Gonzalo's PoC here. Oh, sorry, these interfaces, our attack contract is going to use. So for our test structure, we're only going to need this ERC20 actually. So let me just change over this counter file to our attack contract really quickly. Starting with a brand new contract here. And our attack contract is the one that's going to be interfacing with these other on-chain contracts. So let me move that here and make our test a little more simple. This also needs the ERC20 interface. Okay. So yeah, so let's make the test a little more simple. So what should our test do? Well, our test should first deploy our attack contract. It should set up any of our constant values that we're going to be using in our attack. So what tokens are we attacking? Where does sushi swap exist? Where does curve exist? So let's go ahead and set up an instance of our attack contract. So you're going to have to import our attack contract here from this source directory. Source attack contract.sol. Now that we've imported the attack contract, we can define an attack contract object in our test contract, call it attacker. Some other constants that we're going to need, USDC. Again, I'm going to copy over these values just to make it a little more simpler from Gonzalo's PoC. So if you need these values, go ahead and check out that link. So this is the address of USDC on Gnosis chain. We're going to need the address of wrapped xDai. Oh, WXDai. We are going to need the address of this 100 finance wrapped USD, so HUSD. I need the address of 100 finance wrapped xDai. And we need the address of the Uniswap router. Okay, so when a contract extends this test object in Forge, we have a few functions which automatically run for our test. So anything called test something. So if you define some function test attack, whatever's after this test doesn't matter. As long as it has this beginning test, that's what Forge is going to run. We also have access to a setup function. So if we call this function setup, this is going to run before any of our tests run. So to set up, we're going to create an instance of our attack contract and pass in all of those constants that we defined. So we set up an instance of our attack contract. And in our test attack, we're going to call attacker dot, and this function doesn't exist yet, but we'll make a function called attack that initiates this attack on 100 finance. So this is our very simple test to first set up our constants that we need to reach out to different Gnosis chain contracts, create an instance of our attack contract, and then initiate the attack. So this attack function we need to create in our attack contract. Find attack. It is external. And when we initialize this attack contract, we're also passing all these parameters, and these parameters will be passed to the constructor in our attack contract. So we need to define a constructor as well. The constructor is going to take that USDC address, wrapped xDie, $100 finance USD, $100 finance xDie, and the router. And let's go ahead and set up these as global variables in our contract, so our other functions can have access to these more easily. So if we remember, we imported the ERC20 interface here, so we can define this USDC as an ERC20 object. Similar to how the Uniswap v2 router here, we're importing the interface here, and we're defining this router variable as Uniswap v2 router, and that just lets us call those functions directly on the router object. So we have to set those in our constructor. Okay, so our constructor takes those values from our test, saves them in the contract storage, and then those values we can use in our other functions. One little side note, since these variables are immutable, that means they're essentially constant, and these values are going to be baked into the contract itself. It's not technically reading from storage, but that's not super important. Okay. So we've gone through some setup. Let's start writing out a high level of our attack. So if you remember, let me actually pull these steps into our attack contract. Our first step is to flash loan funds from SushiSwap. So we need the SushiSwap factory. So we're defining a Uniswap v2 factory object. We're then casting the result from router.factory. And this router.factory just returns the address of the factory. We're casting it to a factory object, and that gives us our Uniswap v2 factory. We then need to find the pair contract for wrapped xDie and USDC. We find that through the factory. So let's set up the pair object. We're casting the result to a pair object of factory.getPair. And we're going to pass the address of wrapped xDie and the address of USDC. So from our factory, we're getting where that pair contract is located. We're then going to define our flash loan borrow amounts. And we want to borrow as many tokens as we can from this Uniswap, or sorry, the SushiSwap pair contract. So we're just going to set the borrow amount to the balance of the pair contract itself. And we'll give it a little haircut of 1. Cool. So we have the address of the pair contract. We know how much we want to borrow. Let's go ahead and trigger the flash loan of SushiSwap. I'm going to do pair.swap. And we want to borrow USDC. So in the pair contract, if token 0, in the pair contract, it refers to the 2 tokens as token 0 and token 1. So this could be in either order. We just want to check that if the pair, if token 0 in the pair contract is wrapped XDAI, that means our first parameter is going to be 0. So we don't want wrapped XDAI. We want USDC. And then the second parameter is going to be the amount of token 1. So this is the amount of token 0 that we want. This is the amount of token 1 that we want. So again, if the first token in the pair is XDAI, this second one is going to refer to USDC. So if the first one, if token 0 is XDAI, then this second parameter here is going to be our USDC. We want to put borrow amount. Swap also takes the receiver of the funds. So we're going to do address this. And then it needs some non-zero data. So some arbitrary data, we're going to do ABI encode some non-zero data. Okay, so this is all we need to do our flash loan from SushiSwap. When you do a flash loan, what happens is when the pool sends you those tokens, it calls a flash loan callback function on your contract to then use those tokens for whatever you want and then repay the loan. So right here, when we call pair.swap, SushiSwap is then a call back to our contract, and we need to implement their specific flash loan fallback function. And this flash loan fallback function is called Uniswap v2 call. So this is the function that lets us use those funds, but we still have to pay them back at the end. So this Uniswap v2 call function takes an address that we don't care about. The more important thing is the amount of token 0 that was sent back, the amount of token 1 that was sent back, and some arbitrary call data. So we just need to make sure we follow the interface exactly, because if we don't have all of these parameters here, SushiSwap won't find the function in our attack contract, and the call will fail. So we first have to figure out which of these amounts we want to use. So amount token equals amount 0. So what this line is saying is if our amount 0 is equal, use amount 1 instead. But if amount 0 is not 0, that's the token we borrowed, so it should be this value. So our total flash loaned, that's this amount token. Cool. So by this point in our attack contract, we have that $2 million of flash loaned USDC. Now that we have the flash loan funds, we need to deposit those funds as collateral in 100 Finance. So for here, I'm going to call this some function called deposit USDC, and we're going to be creating this function. So function deposit USDC. This can be internal since we're only calling it from within the same contract. Deposit USDC is going to need to take our balance of USDC and deposit it as collateral in 100 Finance. So we need to get our balance of USDC. So USDC.balance of, and then address of this contract. So this is our total balance of USDC. We're then going to call on the USDC contract, USDC.approve. We're going to improve 100 Finance's contract to transfer our total balance of funds. So this is just a mechanism of how 100 Finance works. You need to approve it to transfer your tokens for it to pull it into its contract. And then we're going to call the 100 Finance contract HUSD with .mint, and attempt to mint HUSDC equivalent to our USDC balance. So this mint function will give us back those those HUSD tokens that we can then use to borrow funds later. Okay, so that's all we need to do to deposit our USDC as collateral in 100 Finance. 100 Finance sees that we've deposited this USD, and now we can go ahead and use that deposited USDC as collateral for a loan to borrow from any other market. So to trigger the borrow, so we've called this deposit USDC function. It's minted those 100 Finance tokens. After deposit USDC, we're going to call some function borrow USDC. So this function is going to borrow USDC against that HUSDC we minted here. And this borrow, remember, is what's going to trigger that on token transfer. So let's write that function borrow USDC. This can be internal as well. And we want to know how much we want to borrow. So we'll do, we have our total borrowed amount. Let's see, total flash loaned, sorry. This should be a global variable so that we can access it in our other functions, total flash loaned. We're going to take our total flash loan amount and multiply it by 90%, essentially. So the reason we have to multiply it by 90% is we can't borrow the total amount that we posted as collateral, because remember, we need to over collateralize positions in DeFi. So we just need to borrow a percentage of the amount that we collateralized. So we take that amount, we call out to 100 finance again, call out to that HUSD contract, and we just call dot borrow, passing the amount. So this is all we need to do to trigger that borrow in 100 finance. And this is where 100 finance is going to call back into our contract when transferring us the USDC we're borrowing. So we're still in this flash loan callback function. We've called deposit USDC. We called the borrow USDC, but within borrow USDC, 100 finance is calling back again into our attack contract, and that we now need to implement the callback on token transfer to continue the execution flow. So let's go ahead and implement the function on token transfer. And on token transfer takes an address from where the token is coming from. Takes a UN256 amount of token. And then again, it takes some arbitrary bytes. So in this on token transfer, we've already been transferred this USDC that we're borrowing. Now we want to borrow again before our debt is updated. So in this on token transfer, so this triggers anytime we receive the Gnosis chain wrapped bridge tokens. So the first thing we want to do is make sure that we're only calling our reentrancy logic when 100 finance is transferring tokens to us. So let's go ahead and make sure that the contract calling this is not the Uniswap pair from when we do the flash loan. So we're going to do I Uniswap v2 factory. We're going to get the factory again. And again, we want this factory so we can get the address of the pair contract. And the pair contract that we want the address of is wrapped XDAI and USDC. So this is that pair contract that we borrowed from. We don't want this attack logic triggering when we take the flash loan. So if who these tokens are being transferred from is not the pair contract, then we're going into our attack logic. We also only want this to trigger once. So we could borrow multiple times, but for this demonstration, we're just going to borrow USDC and then borrow XDAI before our debt is updated, and then just end it there. So we're going to create a Boolean which checks if XDAI was already borrowed. And that's going to be a global variable. And in here, we're going to execute our attack, our reentrancy attack. So we're going to do borrow XDAI. So this function is where we're going to re-enter 100 Finance's contracts. So what does this borrow XDAI look like? Well, it's going to look a lot like borrow USDC. So let's create the function borrow XDAI. In borrow XDAI, we're going to set borrowed XDAI borrowed to true, so we don't we only do this once. And then the amount of XDAI we're borrowing, remember we need to calculate it based on the collateralization ratio. So XDAI actually, I think, has a higher collateralization ratio or like a smaller pool of assets. So instead of trying to borrow 90% of the amount that we collateralized, we're going to borrow 60%. And the other thing to note here is our total borrowed is in USDC, which USDC token goes up to 6 decimal points. However, XDAI uses 18 decimal points. So we got to remember to adjust this value for that as well. So we're going to multiply it by 10 to the 12th, 1e12. And this is the amount of XDAI we're going to borrow. So again, we need to call out to 100 Finance, our I compound token. Sorry, it's not HUSD because we're not trying to borrow USD anymore. It's HXDAI because we're trying to borrow XDAI. Again, remember we have to borrow from different markets here. We've already borrowed a lot of USDC. And then we pass the amounts. So once we've called borrow for XDAI, we've already exploited this vulnerability. We borrow USDC, 100 finance, we call 100 finance.borrow. In this borrow function, it's transferring the bridged USDC back to us, which triggers this on token transfer. So this function hasn't finished yet. We trigger this on token transfer function. We call borrow XDAI, and XDAI is borrowed before our total debt is updated. So we're doing 2 borrows before this first borrow finishes, essentially. Cool. So yeah, so execution flow of this borrow should have ended. So let's go back to where we called borrow USDC. Now we're back at the end of this function here, and we need to continue on. So we've already borrowed more than we should have from 100 Finance, but we still have to repay that flash loan. Remember, so we've flash loaned those funds, we've deposited them as collateral, we've borrowed against that collateral and re-entered 100 Finance, but now we need to repay that flash loan so that our whole contract doesn't revert. So when we took that initial flash loan amount, we borrowed USDC. And when you do a flash loan, you need to pay back in that same asset. So we have a lot of USDC, but we don't have enough to cover the initial amount we borrowed because of that collateralization ratio. We had to borrow less USDC, and we have XDAI. But we have a lot of XDAI as well. So to be able to pay back that flash loan, we need to convert our XDAI to USDC so we can pay in the full amount of the flash loan and then get away with whatever's left over. So let's implement that. We'll do swap XDAI, and this is going to swap our XDAI for USDC. And this is actually going to swap the XDAI for USDC on the curve pool. So the reason we need to use the curve pool is because SushiSwap's pair contract has reentrancy protection, and we've already called into it to flash loan those initial funds. So we can't go in and swap the XDAI for USDC in that pool anymore because we would trigger the reentrancy protection and the whole transaction would revert. So we need to use an entirely different pair contract or token pool or exchange. So we're going to use Curve for this. So that being said, I didn't actually set up the Curve contract. We need that address here. So I'm going to set that up in our test framework. So address curve equals, and we'll go ahead and copy over that address. And here it is. And we're going to pass that into our attack contract because the attack contract needs to know it. And that means we need to modify our constructor. That's going to also take the curve, the address of curve, so we can trade those tokens. And let's go ahead and set up the interface for curve as well, so we can more easily call those functions. And all the interface for curve needs is this exchange function. That's like our sushi swap. That takes an integer of 128 bytes, a second integer of 128 bytes, an unsigned integer of 256 bytes, dx, and an unsigned integer 126 bytes, min dy. So this is our assets, and then the amount out and our minimum, sorry, our amount in and our minimum amount out. Okay, so we've got that interface for our curve contract. Going to create that global variable so we can use it in our functions. Curve. And there we go. So now we have access to this curve object. We can use it in our swap xDie function. So let's write that swap xDie function. So swap xDie internal. We need to actually wrap our xDie first because curve pool only can only handle ERC20 tokens. And if you remember, xDie is the native asset of Gnosis chain. So it's a lot like ETH is the native asset on Ethereum. Curve needs the token to follow the ERC20 interface. So first we need to wrap it, and there's a convenience wrapper very similar to Weth, which is Weth is wrapped ETH. We're going to wrap our xDie. And that's another interface we're going to need. Sorry about that. So we have iWeth, interface, iWeth. That's going to have one function called deposit. So now we have our interface for wrapped xDie. This is our address of the wrapped xDie contract. We're going to call deposit and pass the balance of this contract. So this is going to wrap all of the xDie this contract borrowed. And we can now approve 100 Finance's contracts, or sorry, not 100 Finance, Curve's contracts to transfer our xDie to then use it in that exchange. Oh, so now that we've approved, we need to call out to Curve, call curve.exchange, asset token 0 for token 1. our wrapped XDAI balance. And we don't care how much we get back from this. We're just trying to convert to USDC. So our min output is going to be 1. Cool. So really quick overview. The swap XDAI, we're taking our XDAI that we borrowed. We're swapping it back for USDC. So now that we have the USDC, we could finally pay off our flash loan so this whole transaction doesn't revert. So we are now at the end of the swap XDAI function. We need to repay that flash loan. Now there is a fee when you flash loan funds, but it's relatively small. I think it's 0.03% or 0.3%, something like that. So it is larger than what we borrowed, but it's negligible compared to the amount of funds that we've stolen. So let's create an amount repay. It's going to take the amount of token that we flash loaned. We're going to multiply that by 1,000 divided by 997 plus 1 to account for rounding. So yeah, so 0.3% fee from SushiSwap to flash loan these funds. And then we're going to call USDC.transfer message.sender amount repay. Now, the reason we're transferring funds to the message sender is because, remember, this function is the callback for flash loans. So the caller of this function is going to be SushiSwap's contract, and we want to transfer this amount of USDC back to them so that they see that their flash loan has been repaid. Awesome. So that was our last step of our attack. So with that flash loan paid off, to prevent our whole transaction from reverting and undoing all of our hard work, we've finally finished our PoC for the 100 finance hack, which led this attacker to draining all $6 million. Let's review really quickly all of these steps because I know there was a lot of different things going on. So really quickly, before we run this, we have our test contract, which sets up our necessary addresses for the tokens that we're using for this attack. USDC, wrapped XDAI, 100 finance USD, and 100 finance XDAI, our SushiSwap router, and the curve contracts. So we then set up an instance of our attack contract, passing all those relevant variables. And then our attack is run in this test attack function. So if we go to our attack contract, the attack contract finds the pair for wrapped XDAI and USD, flash loans the entire balance of the pair contract in this pair.swap. So this is where the flash loan is happening. When the flash loan occurs, SushiSwap calls back into our contract, and we can use our funds here that we flash loaned. We first deposit USDC to 100 finance. We then borrow USDC against that collateral. And within this borrow USDC function, our on token transfer callback is being called, and we're borrowing XDAI against that same collateral again. So after this borrow USDC has completed, we've exploited 100 finance. We swap the borrowed XDAI for USDC so we can repay the flash loan and finally actually do the repayment of the flash loan. So I'm actually going to add a couple console logs to this so we know what's going on as well. We're going to add a console log for after we borrow XDAI. Going to add a console log to when we borrow USDC. And we're going to add a log, console log when we borrow from flash loan from SushiSwap. That's going to happen in here. So this may not work on the first try, but to run our test now, you can run forge test. Again, these functions in our test contract are going to be run when we do that. So we write forge test. We pass it the URL of our provider, and we exported that as fork URL. This is going to be the URL that you get from QuickNode. And then for this POC, we need to fork from a specific block number because this attack was already exploited. We're basically reversing time to before it was exploited so we can demonstrate this. So our fork block number is going to be 211200000. So this is a block just before the exploit occurred. Okay, so we'll go ahead and see what errors we have. I'm sure there will be errors. Missing identifier. Uniswap v2 router. It's an interface. Yeah, so I'm missing the I. Our console log is missing. Yep, we forgot to import our Forge STD console in our attack contract. Let's see, total borrowed. Misspelled a couple things. Let's see, total borrowed should exist. It does not exist. So let's make an unsigned integer of 256, total borrowed. We misspelled address here. Gotta fix that. Where is that? Here we go. We need to cast this. We also need to cast these others addresses to the object we want. So these are ERC20 tokens. Forgot to cast these because these are being passed in as just the address. Okay, some more errors. Yeah, this is very common when writing POCs, is reverting transactions. So let's see if we can figure out what's going on here. We have one failing test. Let's go ahead and print out some more information about what's going on here. We can print more of the stack trace, I believe with doing -v, and the more V's you add, the more verbose the output would be. So if we take a look here, this is our execution flow. It looks like this swap, there's an issue with the SushiSwap call. Or no. Fatal external error. Let's go ahead and compare our written code to Gonzalo's POC and see what we're missing here. So we have our attack function. We're setting up our factory. We are getting the sushi swap pair. Our borrow amount is the balance of the pair. We are executing the swap, which triggers the flash loan. So now we're in the Uniswap v2 call. We are calculating the amount flash loaned. This looks okay so far. We first deposit USDC. Let's take a look. Deposit USDC. We're depositing in this USDC balance. We are approving 100 Finance to use our balance. We're calling mint. Let's try and add a console log here. Okay. Okay, so let's look at our console logs at the top here. So we did borrow the entirety of the USDC pool. It looks like our 100 Finance collateral was deposited. Maybe an issue with borrow USDC. Okay, so an issue with our on token transfer. Right, so this borrow goes into our on token transfer. Let me see if I made a mistake here. Ah, okay. So, right. Okay, so it looks like we're failing in this on token transfer, in which we're borrowing XDAI. So when we borrow XDAI, it's transferring that native asset to our attack contract. And to be able to receive the native asset, our attack contract needs a receive function. So contracts aren't natively allowed to receive some asset. There are ways around that, but unless if you're doing a transfer, a normal transfer of the native asset, which in this case is xDie, we need to implement this receive function. So let me go ahead and add a console log here as well, make sure that that is working. So yeah, this is likely reverting when we were borrowing xDie because 100 Finance wasn't able to send it to our contract. Okay, so we got a little further. Interesting, we received 0 xDie, so that doesn't seem right. Am I forking from the correct block? Yes, I believe so. That's really strange. Let me console log this borrow amount. Okay. Yeah, total borrowed should not be total borrowed. This should be total flash loaned. Total borrowed doesn't exist in our contract. We never set that. Total borrowed, let's see. Yep, that was my bad. I renamed that variable to total flash loaned. So total borrowed was 0. We were trying to borrow 0 xDie. So here we go. What is the next problem? Oh, it's okay. We are past test. We just proved the existence of the vulnerability. So let's take a look at this. We first borrow 2 million USDC from Sushi. We then deposit that USDC as collateral in 100 Finance. We borrow USDC against that collateral. We then borrow xDie as well against that same collateral with that reentrancy vulnerability that we talked about. And then finally, we repay that flash loan. And then as we can see here, our USDC balance after all of this is a large amount. So I think this is around 2 million. No, yeah, almost $2 million. And that's with next to no starting capital. So you can start to see kind of the power of flash loans for malicious actors. They are a really interesting financial tool, but they can also be used maliciously. But hopefully you can take away kind of how you can use flash loans in your future POCs and kind of get a better understanding of how to write a POC and debug issues you're having with Forge.